Welcome back. We are at the second page here. This is video 2 for 5.3. So we're just going to continue on with that. So here's our formula that we just derived above for the average value of a function. Now, when we say average value, if you're measuring temperature, it means average temperature. If your function f is measuring velocity, then this could give you the average velocity. So depending on whatever you're measuring, that's why they kind of generically say average value. Average value. This is not to be confused with the average rate of change, which also has the word average, but is a different formula. This one's f of b minus f of a over b minus a. Very easy to get these confused. They're both related to mean value theorems. This one's related to the mean value theorem of derivatives, the MVT, the main MVT, versus this one comes from the MVT of integrals. So we will practice how to distinguish them as the year goes on. So let's say we want to find the average value of the function y equals x to the third power on the interval from 1 to 4. So the average value, in this case, a and b are the starts and ends of the interval. So 1 over b minus a times the integral from a to b of our function, which in this case is x cubed. So this is 1/3 times this definite integral. And I'm just going to go ahead and do the integration and then I'll evaluate it. Maybe I'll even put some brackets here to just make sure that we are clear that that 1/3 is a multiplier that I'll use at the end. So this would become 3x squared. Actually, I can leave it like this. And then, I did a derivative. Shame on me. Let's try this again. X to the 4th divided by 4. And then I'm going to evaluate this from 1 to 4. Now, what I can do if I'd like, and I like to do this, I think it makes the computation just a little bit easier. So I would multiply these multipliers, these constant multipliers, and get a 1/12. And I would just pull that out of the evaluation process. And I'm going to evaluate this expression to the power of 4 to the power of 4, minus 1 to the power of 4. Now, you could only do this if the multiplier is multiplying the entire expression. So be careful on how you use that. So this would be 1/12 times, let's see, 256 minus 1 would be 255. And I believe that could reduce. I think I can divide these both by 3, which would make this, I think, 85 over 4 if I didn't make a computational error. Now, what does that mean? This means that if I look at the function x cubed and I look on the interval from 1 to 4, the average value or the average height or the average output of this function is 85 over 4. Well, what's that? I don't know, 21-ish, 21 and a little bit. So the average height is right in here. This is the average value or the average height. If I look at all of the heights that occur and how frequently they occur, that's the average height or the average value. All right, why don't you try example 2? You can pause the video and then restart it once you've had a chance to try it. Using that same formula, average value or average output for this function should be 1 over b minus a times the integral from a to b of the sine of x dx. So 1 over pi over 2, when you divide by a fraction, you can multiply by the reciprocal of that fraction. And then the integral of sine, be careful here, is negative cosine of x. And that needs to be evaluated at 0 and at pi over 2. So be careful here because it's very easy for kids to put cosine x, they take a derivative instead of an integral. I'm going to multiply this negative by the 2 pi and pull that constant multiplier out. And I will do the cosine of pi over 2 minus the cosine of 0. And so the cosine of pi over 2 is 0. The cosine of 0 is 1. So this would simplify to negative 1 times negative 2 pi, which is, or 2 over pi, which is positive 2 over pi. Number 3, a strictly increasing function. That means it is only increasing. It is never decreasing or constant. Has the values as shown below. Use a left endpoint Riemann sum with 3 subintervals to approximate the average value of this function on the interval from 1 to 10. Well, remember, average value, and it's on this interval, 1 over b minus a times the integral from a to b of this function, which we're calling f. Well, we don't have an equation here, an expression for f, so we would need to approximate the integral portion of this expression. So what I'm going to do is I'm going to say, okay, I have this 1/9 that I will multiply at the end, and kids often forget that part. And then I'm going to go ahead and do a Riemann sum as indicated. They said 3 subintervals. We got a space missing in there. In order to then figure out what the integral portion is, and then don't forget to divide that by 9. Okay, because this is an average. Average, you have to make sure you're dividing. So that 1 over 9 is the same as dividing by 9. All right, I need 3 subintervals. 1, 2, 3, 4, 5, 6, 7. I'm thinking something like this. Now, when you're making these subintervals, yeah, that would work. You want them to have the same number of columns in each one. Each one of these would have 3 columns. And remember, wherever you leave off, you start off at the same place. These are right adjacent to each other. There is no gap. So you always want, like that 4, I'm going to use, that 0.47 I will use in 2 different rectangles. Left endpoint, remember, you want to calculate the width. The width here is 4 minus 1, which is 3. The width for this one is 7 minus 4, which is 3. And the width for this one is 10 minus 7, which is 3. Since they have the same width, I could actually multiply by the width first, and then I just need to, for each one of these, pick the correct height. There are 3 heights to choose from here in this first rectangle, but I want the height on the left-hand side, so I would use a height of 2. For the next rectangle, again, there are 3 heights here represented, but I need to use the height of 7, the one on the left, for that interval. And then for my last rectangle, I will use a height of 15, because that's the one on the left. So if I simplify this, I'll just do 3 times, divided by 9 is 1/3, times 9 plus 15 is 24. 24 divided by 3 is 8. We are going to use a calculator for number 4. The number of inches of rain in a 1-month period in Spokane, Washington can be modeled by this function r of t equal to 1.5 t to the 3rd power minus t minus 14, where t is the number of months after February. Oh, that's an interesting, whoops, thought I was highlighting. Number of months after February. We do need to pay attention to that so that we can correctly interpret that portion. We want to find the number of the average number of inches of rain in Spokane. Spokane? In Spokane. So remember, there's average value and there's average rate of change. I'm not asking for the average rate of change. I'm not looking at how the rain is changing, the rainfall. I'm looking for the average number of inches of rain. That's average value, because the function r measures the number of inches. So I want the average number of inches. This is r. I want the average of r, or the average value. I'm going to set this up by hand, and then we will use the calculator to actually compute this. First of all, I better figure out what A and B would be. So we're going from April to June. Now, you don't want to overthink this next part here. This is common, and we're just going to agree upon this strategy for the rest of this year and also for your AP exam. April is 2 months after February. Don't get confused on like, was it the start of April, the end of April? We're just going to say April's the 4th month, February's the 2nd month, so it's 2 months afterwards. June is the 6th month, which would be 4 months after February. I'm just doing 6 minus 4. If you want, you could really count. I guess you could say March, April, May, June. So we're not worrying about like, is it the start of the month, the middle of the month? We're just going to say just the number of months, subtract them off. That's A and B. So as I do my average value, I'll do 1 over B minus A times the integral from A to B of R of t dt. This is actually the only work I need to show on my paper. This is the only work I need to actually show on my paper. The rest of this I can do with my calculator, which I, of course, forgot to turn on. So we might have to sit here for a moment while I wait for that bad boy to turn on. But again, you don't need to actually write out the expression for R. You can just write R of t dt for your work. The rest of this you're going to be doing on your calculator. Let's see if it's open yet. Free trial. Let's do the free trial. Okay. So you might remember that when you are trying to type in a definite integral, that there's a shortcut for it. Now, I don't want to forget the 1/2 that's in front, or the 1 over 4 minus 2, which simplifies to 1/2. So I'm going to do 1/2 times, and now I'm going to do my integral, which is shift plus. And this definite integral is going to go from 2 to 4. And I could have defined R of t in a different location if I wanted to, or I could just type in the expression. 1.5 t to the third power. I'd like you to notice I'm doing the actual expression for t. I'm not changing the expression for t to a derivative or an integral. Sometimes kids do funky things there. Minus t minus 14. And then the variable that I'm using is t, so dt. And I get 28, which is a very unrealistic answer. But this would be around 28. 28 inches on average according to this fake made-up model that I made. And this is actually even exact from April to June on average. So, which would be a lot of rain. I mean, they do get a lot of rain up there, but wow. So when you're thinking about this particular type of problem here, make sure that you are not missing that word average. Or it's very common for people to forget the 1/2 and they get 56 inches. Okay, I'm going to stop this video right here and restart the next video where we'll start with the second fundamental theorem of calculus.